All right, so let's try another one. So there exists a set of 3-bit codes, and given a 3-bit guess, the Oracle will flip the response if the guess is one of the 3-bit codes. So if I give it a black, white, black, it will give me the guess back, black, white, black, but the response will be black or white based on whether or not this was one of the secret codes. Okay. So imagine that there are 4 secret codes, 000, 010, 110, and 111. So 011 is not one of the secret codes, and so it will not flip its response. Okay. 110 and 010 are in the set, and so for each of these, regardless if I start out with a black or a white, when I give it one of these, it will flip the response. Okay. So that is how the Oracle works. All right, so using this Oracle, we want to figure out whether there are 0 or 4 secret codes. We have some piece of information that's told us that there are either 0 or 4 secret codes, and we need to figure out which one it is. So go ahead and think about this, pause the video, and see if you can come up with an algorithm, and then we'll go through it together. Okay, so let's go through the algorithm. We just try randomly, or we can go in sequential order. It doesn't matter what we choose as the order. However, once we find 1 secret code, we know it's not 0 secret codes, so we know we've got 4 secret codes. The other way is that once we reach 5 non-secret codes, we know we can't have 4 secret codes. So I can either, so I just test in any order I want, and it's until I find 5 non-secret codes or 1 secret code. So in the worst case, it takes 5 probes, which for a total of 8, that's half plus 1. And so if we had a larger problem with 10 bits, so 2 to the 10 combinations, we would have to go to 1/2 plus 1. So this is a linear time algorithm, just like the last one was. Last one was linear time on the number of bits. This is linear time on the number of combinations, which is actually a lot larger than the number of bits. And so we would like to see a faster one. All right, so let's look at what we do. This will be, again, familiar. We'll put in 3 white balls and have a black ball for response. And this time it looks like it's the same, that we might be doing phase flips, but it's not actually the same because we don't have any knowledge of C-naughts inside. So we're not using phase flips, but we are putting everything in superposition so that there are all possible combinations. And so what it turns out is that if there are no secret codes, then the output will be all whites. But if there are 4 secret codes, then some of the outputs will be non-white. Okay. So let's look at an example where there are 0 secret codes. Let's look at what happens if there are 0 secret codes. So if there are 0 secret codes, the Oracle does nothing. Okay, because I gave it white balls and it's going to give me back white balls, and it doesn't flip the response. So I get back all white balls. What I want to figure out is what happens when there are 4. So I'm going to use these 4 codes, and we're going to go through what happens. And I must admit that this is quite dense. So what happens, I need to put these in a 4-bit combination, set of combinations. And so what I end up having is I have this negative state at the end. So I have these combinations where I have all 8 combinations of the first 3 bits. And then I have 16, because then we have 2 choices. We either are negative phase with a black ball at the end or positive phase with a white ball. So you can see in all of these choices, whenever the last one is a black ball, I have a negative phase. So I have these pairs. These 2 are the same in the first 3 bits. They're only different in the last one. Same with these 2. These are the same in the first 3 bits, only different in the last 2. So we have them all paired up. And these are our 16 states going into the Oracle. And recall that what we would need to do is put each one of these individually through the Oracle. And what we know about how the Oracle works is if it is one of the secret codes, it will flip that last ball. the color of that last ball. So there are 4 of them, 0, 0, 0, which is down here. So this pair will get flipped. 1, 1, 1, this pair will get flipped. 1, 1, 0, this pair will get flipped. And 0, 1, 0, this pair will get flipped. So let's look at that happen. Okay, so those are the 4 pairs that got flipped because those are the secret guesses. And so what ends up happening is the phase of those 4 pairs get flipped. Okay, it's not a phase kickback, but it did flip the phase of those particular ones. Okay. All right, so it turns out that if I use algebra to factor out this same state, the negative black with a white, we can do this, and we'll end up with 8 combinations, and anywhere the phase flipped on these, we're left with a negative phase. So the 4 that are the secret codes now have negative phase for this combination of 8. Whereas when we had all white balls going in and there were no secret codes, it didn't flip anything, which is why we then end up with white balls coming out. But here we have now some negative phases, and we have to figure out what those negative phases do. How does that turn into a black ball? Well, we know that black balls result from things going through H gates, okay? But this looks like a little bit of chaos because we don't know how that's going to factor out into 3 individual bits and which ones are going, whether there will still be ones with negative phase or not, okay? So let's break this down a little bit more and make sure if this isn't, if this seems confusing to you, you can always do it on paper. You can show more steps, and you can always repeat the video. Okay. All right, so let's look at just one of these sets of 3 going through an H gate. Okay, so I have white, black, black, and I put all 3 of those individual bits through the H gate, and then I have all of these 3-bit combinations that are from the tensor product of these 3 superposition bits. Okay, and then some of these are going to may cancel out in the end. Okay, so then what I do is I put each set of these 3 through these gates, and different sets are going to have negative signs on different sets of 3. Okay. So when I'm multiplying them back out, so this one has a negative on the outside, and so I do my internal calculations, and then I distribute that negative sign and negate all of them. Okay. So if I have a positive one, I just do the H gate straight, and I multiply everything out and into the different combinations, right? So this top one is the black ball from all 3, and there were 2 negatives, so that canceled out and became a positive. This one, black, black, white, drew the black ball, and the white ball. So that was only a single negative, which is why it retained a negative. So basically in this set of 8, we will have a negative sign if only one of the last 2 are black. So black, white, white, black, white, black. But if both are black, the negatives cancel out, and if both are white, there were no negatives to begin with. Okay? So we can use the same logic throughout. This set of 3 has only one negative sign on this middle black. So any state that has that middle one being black, which is these 4 states, will have a negative sign. And all of the ones that have that middle state being white will be positive. Okay? But then I distribute the negative sign, and now the top 4 are positive and the bottom 4 are negative. So we would go through, for each of these sets, we would calculate all the positive and negatives for each of those sets. Okay? And then I've lined them up differently so that I can easily see here. I can line up all of the like ones. And so, and notice that just because this one up top had a negative, it doesn't mean that internally it's negative. So we couldn't do a shortcut that said, oh, well, these 4 are negative, so those are all going to be negative. Okay? But we do notice that in some of these rows, like this top row, there are 4 negatives and 4 positives. So those are going to all cancel out. Those are all gone. We have another row, 4 negatives and 4 positives. So these are all gone. Okay? So now it's impossible at this point to have all white balls. Okay, because we don't have all possible states left. And spoiler alert, these 2 rows also are half and half, positive, negative. And so we're left with these 2 rows up top and these 2 rows on the bottom, where some have been canceled out and some have not been canceled out, okay? At the end, we ended up with 4 states left. It's impossible to take these out to the original 3 qubits, and that's okay. That means that they're entangled. So we ended up with 3 entangled qubits. And what we also notice is that all of these 3 ball combinations have a black ball in them. So that's the reason why we're guaranteed not to get a white ball, is because interference made it such that all of the 3 white ball combinations were no longer possible. And so anything we read out will have a black ball in it, guaranteed. So in the first algorithm, we used phase kickback. And in the second algorithm, we used interference. Okay? So in summary, one paradigm for developing algorithms is using these oracles, which are already used in classical computer science for cryptography and security purposes. But it turns out it's even more critical for quantum computing. And operating on multiple superposition states simultaneously is the key to performance, and we saw that in both algorithms. Bernstein-Vazirani used phase kickback to obtain information from those CNOTs because we were told there were CNOTs inside. Whereas Archimedes, we weren't told what was inside. We used the oracle just as a blind oracle. And we used interference to change the mix of the states left. So it got very complicated with lots and lots of states, but many of them were negative and many of them were positive. And so a lot of them canceled each other out.